So the next talk is a professor of cognitive neurology and lead for the neurotherapeutics group at UCL. And his main areas of research have covered post-stroke alexia, aphasia, neglect, and brain behavior relationships and therapeutic delivery of therapy apps. Thank you.
Okay. Oh, sorry, shouldn't have done that. Oh, that was me. I just because I wanted to get onto the. Sorry. Well, thanks for inviting me, Fatima and Richard. And it's so nice to be able to talk, hopefully, in front of so many friends and colleagues. I'm going to start with an apology, really, because I've changed my title. When I was asked to give the title, it was quite a while back, and I didn't really think I was going to have any data to show you from our study. But the good news is I have got some data to show from the study, so I'm going to focus on that today. So if I could do some, yeah, it's just getting rid of those pop-ups was annoying me a bit, but I think I can.
Something's changed. I don't know.
Something's changed. I can just move it down.
Okay.
And
What did you press?
I'm sorry. Sorry.
Oh,
I think I know what I did. Let me, if I go back, sorry, it's a waste of time, isn't it? I think I did it in PowerPoint. That's the problem. Let's start again. Yeah. Give I screen share and pick my one. Is that the one? Yeah. Share.
Press from there.
Yeah.
Your presentation. That's not your presentation.
Yeah.
That's gone. Closed it. Go back to this folder.
Sorry, everybody.
Back to that folder.
And then press this one. Okay, right. Let's move on. So yeah, I'm gonna talk about a small phase 2 study today. There's been talk about how naming some of these cognitive conditions is not terribly helpful. I actually think it's confusing, and we've seen that with a few. And I also think it's true with this condition called neglect, which I don't like to use. And I was speaking with Masood earlier, who's been involved in this project. And I often use visual spatial attention, which I'm not sure he loves. There's also lateralized inattention, which has its problems as well. But I kind of think we know what we're talking about. I haven't got a slide to show you what an example of visual spatial inattention. I assume that most of you will know, but it means that when you've got an array of stimuli in a competing visual environment, patients with this condition are more likely to respond to stimuli on one side of space compared to the other, usually the left. And it depends how many stimuli they are, how complex the environment is. So it varies with the complexity of the environment. Like a lot of the other conditions that have been talked about today, compared to patients who don't have this condition, the patients are at greater safety risk, have lower functional independence scores, longer length of stay, and less likelihood of being discharged home. The condition does improve with time. I mean, when you look in the papers, people will say that it's up to 50 or 60% of inpatients with stroke have inattention, and I don't think that's right. This is from a large series from many years ago. I think this is a bit closer, about a quarter of patients maybe. Of course, you have to look for it to find it, and you can see that over time this improves a lot, which is great. But one of the downsides and one of the problems with neurological rehabilitation is that a lot of the therapy is given early on in people's journeys through after their stroke. Which I think is incorrect, but that's a reason to treat inattention sooner rather than later, because they get most of their therapy while inpatients and then a little bit of therapy in the first few months as an outpatient. And the inattention, which can, of course, affect interpersonal space, causes problems if they have, for example, a coexisting hemiparesis. So that's the reason for focusing attempts on the acute phase. So there's a variety of interventions, and I'm going to tell you about our intervention study. I haven't got time to go through all of these, but it really started with sensory stimulation, prism adaptation, drugs, which I'm going to talk a tiny bit about, and Masood's done quite a lot of work on this, and then eye movements, which is what I'm going to, it's what we based our intervention on. And the reason for this is a paper by Kirchhoff and others, and what they showed was using a sort of laptop screen here and a therapist delivering the therapy into inpatients with this condition, that there was a difference between moving stimuli, which induces smooth pursuit eye movements. So it does require a bit of attention, And the patients have to look at the screen and then follow. Once you lock on a target, your eyes are automatically drawn by these sort of ancient reflexes, ancient cortical reflexes of smooth pursuit, and your eyes follow the stimuli. And eye movements are very tightly controlled to the brain regions that control visuospatial attention. And then the control here is a visual scanning task, and here the patient has to initiate their own saccades. And of course, in this situation, they will tend to ignore things to the left side if they have a right-sided lesion. And they showed in this study that there was a significant effect of these drifting stimuli. They weren't terribly interesting stimuli, but it did still work. And you can see down here that they're only going to treat a certain amount of angle of visual space, about 10 to 15 degrees maximum. So we wanted to put this into virtual reality in order to give a larger field of view. So this is showing you an inpatient here taking part in the study. As I've mentioned, this is a phase 2 group randomized control trial, multi-site here and mainly at Charing Cross, a few other sites, looking at the clinical efficacy of this eye movement delivered therapy using immersive virtual reality. I'm just going to try and start the video. There's no sound on any of the videos. So you can see this chap's on the ward. He's using his right hand to move the racket. I'll show you in a bigger version in a bit. But the racket appears on his left. And the important thing here is you can see he is paying attention to the left. His head is turned over to the left. This is the active therapy. And this is really just to show that despite all the cabling, which you can now do without actually, but when we started the trial, there wasn't the cable-free version, that it can be set up for inpatients who are bedbound. So learn to press the right button. So this is the trial. So time is at the bottom here. Most of it's done, or all of it's done really while they're an inpatient. We do a couple of baseline assessments, and then they get 3 weeks of the therapy, and they get randomized into either the active therapy, which is what I've just showed you, the one that produces horizontal pursuits, or a control therapy, which I'll show you in a bit. And then we have outcomes after 3 weeks of therapy. They practice for sort of 40 minutes a day, 10-minute sessions broken up a bit depending on how much they can tolerate. Not all of them can tolerate 4 sessions a day. And then we have a 3-month follow-up as an outpatient, which I'm not going to show you the data for that today. So I've sort of shown you what the therapy looks like, but I'm just going to show you it again. So this all happens obviously in a 3D virtual environment. There are these sort of tennis ball targets, and the patient has control of this racket, which they can only move up and down. They can't move from side to side. And they have to pick up these rare red targets, which are the red balls. Inside the VR headset, there's an eye tracking, and it can detect when the patient's picked up the target, and then the target turns yellow, and there's also an auditory cue, which changes as well. And the sort of reward for catching all these yellow balls, which this is not going to run long enough for you to see that, is that the environment becomes more enriched. So that's kind of the sort of added on gamification that was put in by the games developers who developed the intervention. This is the control. So we wanted to control for as many things as possible. It also happens in a virtual environment. And this is a rather hard version, but they have to shoot apples out of this tree. You can make the apples bigger. This is actually much harder. In fact, some people prefer this because it's a tougher test. But you can see that the only pursuit movements here will be in the vertical domain. Okay, so the trial hasn't finished yet, and the numbers are relatively small, as they always are in these sorts of studies, despite people saying it's a very common condition. So we've got 9 patients in the horizontal group and 12 in the vertical. I'm going to show you on 2 outcome measures. This is the impairment-based outcome measure, star cancellation. It's a fairly classical clinical test used to assess visuospatial inattention, and high scores are good. So the maximum score on this is 54. There's 27 stars to the left and 27 stars to the right. And you can see here, here's the baseline for the horizontal group, and at the end of the 3 weeks of therapy, it has significantly improved. Here's the control group. They also have significantly improved from their baseline score, which is no big surprise because there are rapid changes in this condition over the first few days and indeed weeks after the causative stroke. But you can see down the bottom here, hopefully, that there's a group by time interaction, which is significant. So we've got a significant difference between the 2 types of stimulation, horizontal and vertical. We have another outcome measure, which I'm going to mention and use a little bit later. And this is the Catherine Begego scale. So this is a sort of functional measure of inattention. And this is done by an independent person. So this is done by one of the ward OTs who is blinded to the therapy. This scale goes the other way. So if you have a high score, it means you've got severe inattention. And if you've got a low score, you're normal. And again, you can see the same pattern here, that there's a significant decrease in the horizontal group. There's a decrease in the vertical group too. But again, Statistically, there's a slightly more impressive effect here of time by group interaction. Okay, so it looks promising. The trial hasn't finished yet. It looks like it's working. But one of the things that we're interested in, and lots of people are interested in this, and lots of the talks over the last couple of days have been about this, is how can we predict why do some patients respond better than others? And it's a tricky question, and it's obviously got to do with a lot of things, including where the lesion is in the brain. And Kathy's done a lot of work on that. But I'm just going to talk about behavioural measures. So can we find behavioural measures that will explain the variance across patients? Now, for these analyses, I'm collapsing the horizontal and vertical groups. So you can forget about the fact that there seems to be a difference between those two groups. I'm now collapsing them all together because, as you see, patients generally improved over time anyway. So how do we explain the change scores? And the first thing, in fact, Nelly mentioned this earlier today, the first thing is to perhaps look at your baseline score. Does your outcome score correlate well with your baseline score? Of course, it does. So there's a significant correlation between your baseline score. I wanted to show first, that there is a correlation between the two types of measure that we have. So this is the impairment-based measure, and this is the functional measure. So that's no big surprise. So two different measures of baseline severity do correlate with each other, but not perfectly. Yeah, what I meant to say here is that when people look at trying to explain why some people improve more than others, one correlation that is frequently done is looking to see whether the change score in your outcome measure is correlated with your baseline score. In other words, does your baseline score, is that an explanatory variable that explains your dependent variable, which is your change score in stars? And for all the rest of the talk, I'm just talking about the change score in stars. There's a bit of a problem with this. That in actual fact, in this case, they don't correlate. There's not a significant correlation between the two of them. You have to be a bit careful here because of something called mathematical coupling. And the reason you can see that is baseline score is obviously just the raw baseline score, and the change score is the end score minus the baseline score. So baseline score appears in both terms, and in some cases, to do with the distribution of the variance across those two measures, in some cases you can get mathematical coupling. So it looks like you've got an explanation, whereas really it's really just to do with the fact that you're using the number in both terms. So you have to be a bit careful with that. So one way around it is to do multiple baselines, and another way around it is to use a different baseline score. So when we look at the baseline score on the functional outcome, the Catherine-Bergega scale, and see if this explains the change score in the stars, there's really nothing there at all. So it looks like initial severity doesn't explain very much, or none really, of the variance as to why some people get better than others. So what does? Now, I've been obsessed with the SART for years. I really like it. It's a task that Tom Manley and Ian Robertson came up with, and you've heard other examples of similar tests over the last couple of days. So it's a go, no-go task. And I've been using it in as many of my trials as I can, because I'm convinced there must be something in here that explains response to therapy. And up until this point, it never has. Nothing at all. Now, it's quite a quick test to do, which is one of the reasons for including it. And we imported a version of this into the Vive. So I'm going to show you a little animation, but it's a YouTube video, but it looks very similar inside the headset. It only takes 5 minutes to do, but it feels like a lifetime if any of you have done this. So it's not a terribly pleasant test, and I'm just going to show you what it looks like. So with this, you just get single digits, and you have to press on every single digit. 2 minutes to go, right? Have to press on every single digit, and except if it's a 3. All right. And the great thing about this test is that normal controls are not at ceiling on it. So you've only got about a second, and you have to press on each one, otherwise it goes as a missed trial. Let's press, 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 press. Is it ever going to come up? Oh yeah, and then people will press on the 3. I'm going to go slightly over Fatima, partly because of that beginning mess up. I'm sorry. So there are a variety of things, even though that test only takes, so there's 200 go trials and 25 no-go trials, and these are various things that fall out of it. So just looking at the top, the go trials. So remember here, I'm comparing the 12 patients. We didn't have all of them because we didn't get the test ready in time for the study. I was a bit in a bit of a rush. I wanted to get going with the study. But we've got 23 age-matched controls. So you can see here that the number of times you press a go trial. So the controls are very good, 196 on average of the 200 trials. So the control subjects are very good at this task. Patients not so good. They only get 140 of the 200 trials. So they're missing some of these go trials, probably because it's quite fast. So there's a significant difference between controls and patients there. here there's the reaction time, and again the big difference. The controls are at about 400 milliseconds on average, and the patients are at 600. The way to do this task is to slow down. So this is one of the reasons that patients are not actually as bad as you might expect, because one way to get tripped up all the time is by speeding, which is what most people do. Going quicker doesn't make the test go any quicker. So if you look down here at the no-go errors, the patient, so there's 25 potential no-go errors. The controls are making 10 and the patients are making 8. So they're pretty closely matched in terms of no-go errors. In other words, there's no significant difference between the patients and the controls. And there's a very interesting outcome as you get here called post-error slowing. So what some people do after they've made an error, there's no feedback in this test. So you're not told you've made an error, but some people are aware that they've made an error. And that shows up in a psychophysical measurement, which is over the next few trials, they tend to go a little bit slower because they realize they've gone too quickly. And then they get back into the pace going, oh, this is a really easy task. And then they make another mistake. So you can see here, a score of 100 means on average, there is no post-error slowing. So the controls here seem to get a bit more post-error slowing or error awareness. But you can see that the standard deviations are quite wide. So these are the two measures I'm going to correlate. This measure, the GO trials, is a measure of sustained attention because of the low rate in the patients. And this is something that Ian Robertson has published on, so I think it's okay to use that. And this second factor, error awareness. So we're going to correlate those with the change in STAR scores. So on the y-axis, you've got the change in STAR scores. The higher the score, the more they did, the better they did. And on the x-axis, we've got the percentage of GO trials. In other words, the higher this is, the better their sustained attention. Is there a correlation? Yes. Is it significant? Borderline. Does it explain much variance? About 30%. So there's a hint here, maybe, that sustained attention is perhaps one of the things that might be explaining why the response to therapy across patients, the variability. But we get a better score here with the post-error slowing. So we can see here that, generally speaking, those patients with greater post-error slowing, in other words, greater evidence of error awareness, are ones who respond better to the therapy. I'm nearly done. I didn't want to just mention my own work. I'm on this paper, but I just want to make it clear that I've had nothing to do with the main key ideas of this, which was Edwin and Paresh and Masood came up with. And they did a similar thing. They're interested in which cognitive variables help explain response to treatment. In this case, the treatment is guanfacine, so it's a drug. And this did have a significant effect on patients. This was the within subject. So they did drug and placebo, which was very nice. It wasn't a between group thing like the one I've just shown you. And they showed that guanfacine versus placebo within subjects had a significant effect on STAR cancellation. They used a slightly different test, a cancellation test, and they found more targets on the guanfacine than on the placebo, but it wasn't a lateralized thing. But they brought in a nice thing looking at Bayes factors. And the reason for looking at Bayes factors, it means that, as well as usually with standard statistics, as most people know, you can only reject the null hypothesis, you can't accept it. But with Bayes, you get a probability that the null hypothesis may be true, which I think is useful if you've got a lot of variables and you know that a lot of them are not going to come out. And rather than saying, well, we just weren't sure, you can say, actually, we're pretty sure that these aren't relevant. So they did some nice statistics on that, but I haven't got time to go through them all. But they had measures of spatial working memory, sustained attention, a bit like I just had, directional bias, and also something here called search organization. Again, it was a bit of a small study, but they said there was moderate evidence. This is all using the Bayes stuff. Moderate evidence for the absence of an effect. You can't usually see that in a paper. Moderate evidence for an absence of an effect of guanfacine on the search organization. Also, moderate to strong evidence that guanfacine does not improve response time variability. No conclusive evidence of whether it affects signal detection on the sustained attention task, and strong evidence that guanfacine did not improve spatial working memory. Now, that may seem like quite a lot of negatives, but I think those are actually really important by using these techniques. So I'm going to wrap up quickly. I've shown you evidence from an ongoing inpatient trial suggesting that smooth pursuit eye movement therapy may be beneficial in this condition. Other people have shown that, but we're the first people, as far as I know, to do it within a virtual reality setup. Factors other than initial severity are likely to be important in explaining the variability in response to therapy, e.g. sustained attention and error awareness. I've given you some hints of that. And I do think these Bayesian methods are something that we should all be thinking about incorporating when we're looking at multiple variables, trying to explain response to therapy or changes over time. Thank you very much.
Thank you very much. That was a lovely talk. We have time for one quick question. Can I ask you a question?
You may.
So with our kind of massive IC3 kind of battery, we find that auditory sustained attention loads heavily on all the other tasks. Do you think there's something in this kind of sustained attention in terms of predicting performance and all the other tasks in terms of not just neglect or visual spatial, but just generally how people perform? And do you think that could be a target for therapy, regardless of what deficit you have after stroke?
Yeah, I mean, I think yes is the simple answer. I think sustained is very important, and I haven't looked at the literature in sustained attention in control subjects, and I suspect there's a lot of evidence there for sustained attention and certain ability on certain tasks. But you know, I said I went a bit crazy with the SART and lots of other therapy studies I've done. I think it depends on the therapy. I think this therapy does depend on sustained attention because you've got to sit there for 10 minutes while these balls go past. But I think when you're doing trial by trial therapy, say in aphasia, like confrontation naming, I'm not so sure that sustained attention is as important. So I don't think it's an interaction between sustained attention and the condition. I think it's an interaction between sustained attention and the thing that you're trying to improve and the task that you're using to improve it.
Great, thank you so much. Please join me. Okay, thank you so much. The next speaker, again, doesn't need any introduction, but for newer members who've joined, Matt Lambden-Raff is a world-leading expert in semantic cognition and aphasia. He obtained his PhD from York University and subsequently went to the MRC CBU Cambridge, where he's back now as a director, then went on to Bristol and Manchester, where he was appointed as a professor. He's part of many prestigious societies, far too